this isometric thermal overlay of a standard commercial facility. A building is a dynamic system of potential energy, where invisible heat blooms and vapor clouds wait for a catalyst. Fire prevention requires the active disruption of the elements shown in this 3D fire tetrahedron diagram. You must continuously force heat, fuel, oxygen, and the chemical chain reaction apart. This disruption is the core responsibility of a Canadian fire warden. You are tasked with identifying and neutralizing these spatial hazard geometries before an ignition sequence begins. Basic hazard awareness is insufficient. You must examine the layout of a space and understand how its physical geometry changes the building's specific risk profile. We will break this responsibility down into 3 operational pillars: foundational fuel management, high-energy process controls, and zone-specific hazard topographies. Mastering this facility matrix is the key to preventing a single spark from turning into a deadly cascade failure. We start in the structural foundation and corridors to examine baseline fuel load management. Notice the volumetric red masses in this cross-section. These represent accumulated combustible loads, often hidden in plain sight. Managing this material requires viewing housekeeping as the strict, continuous regulation of your combustible inventory. When unmanaged debris and dust accumulate, they create physical fuel bridges. As this diagram illustrates, continuous combustible dust allows fire to bridge 2 zones. Vertically, stacked pallets create a thermal bridge, radiating heat upward. Lowering them restores a physical gap, providing the mandated clearance radius for sprinklers. Alongside static fuel loads, we have to account for mobile ignition sources, specifically the enforcement of unregulated smoking policies. A rogue cigarette introduces a random high-temperature variable into a carefully measured fuel matrix, bypassing structural fire controls. Controlling housekeeping, storage clearances, and smoking policies neutralizes the passive pathways that allow minor sparks to become catastrophic events. In maintenance areas, we encounter hazards that generate high energy. This wireframe reveals electrical conduits pulsing through walls, carrying power across the facility. When these circuits are overloaded, they enter a state of thermal runaway, generating excess heat faster than it can dissipate. Daisy-chained power bars are prime culprits. This circuit schematic highlights where electrical resistance spikes at the junctions, generating localized heat. As heat radiates outward, surrounding materials degrade, reach their auto-ignition temperature, and ignite. A different physics principle applies to flammable liquids. The liquid itself does not burn. The vapor it emits does. This cross-section of a storage cabinet shows vapor pressure in action. Invisible gas off-gases from the containers, pooling and concentrating near the bottom of the unventilated space. A single static discharge can ignite that concentrated pool. Grounding, bonding, and using fire-rated cabinets are absolute requirements to isolate the vapor from random sparks. Hot work, operations like welding, cutting, and brazing, introduces a high-energy ignition source into your environment by design. That level of energy demands strict geographical isolation. This top-down blueprint highlights the mandatory 35-foot circular safe zone that must be established around a welding station before a permit is issued. Even after the work stops, a dedicated fire watch must remain on site to monitor the area for latent, delayed smoldering that might surface hours later. Managing high-energy processes requires isolating extreme heat vectors from the volatile vapors and fuel bridges identified earlier. General hazards behave differently depending on the spatial geometry and the specific fuel types of an operational zone. In an office environment, a high density of paper and plastics enables rapid surface-level fire spread. Combine that fuel density with localized electrical loads. This X-ray illustration of a standard cubicle shows the concentrated heat signatures generated by space heaters and tangled, frayed charging cables positioned under a desk. The warehouse environment introduces the mechanics of vertical fire dynamics. High-rack storage transforms rows of goods into vertical flues. As the arrows in this elevation view demonstrate, convective heat transfer is accelerating upward through the narrow gaps between pallets, forcing fire growth. That upward draft acts on unique warehouse ignition risks, from hydrogen off-gassing at forklift charging stations to the highly combustible energy profile of shrink-wrapped pallets. In commercial kitchens, the hazard is airborne. This slow-motion visualization tracks microscopic grease particles aerosolizing above a stove and traveling into the extraction hood. Without strict, regular maintenance, those grease particles accumulate inside the ductwork, creating a flammable tunnel running through the building. Should that grease catch fire, standard water extinguishers will spread it. It requires a Class K extinguishing agent to smother the liquid fat through a chemical reaction called saponification. Conducting an effective environmental audit requires you to apply these specific hazard profiles to their corresponding operational geometries. Returning to the macro isometric view of the entire facility, the red hazard zones and orange ignition vectors shift to a stable, cool blue. Preventing catastrophic fires requires understanding how daily operational processes bridge the gap between static fuel and active ignition. Your role as a Canadian Fire Warden depends on proactive systemic vigilance. Auditing spatial hazard geometries is a continuous daily operational requirement. It requires enforcing the foundational policies on housekeeping, hot work protocols, and storage clearances every day. Maintaining the integrity of this hazard control matrix stops cascade failures, protecting both the facility and human life.